Okay. So last time what we did is to discuss systems which were in thermal equilibrium with another system. So we took a system which is in thermal contact with a much bigger system, which we have called the heat bath. And we want to have a statistical description of, we derived a statistical description of this system. And the way to do this is to say that now the energy of this system will not be conserved because it will be exchanging heat with a heat bath, but the temperature will be the same. Okay. So what we want is to have a description where the macro state is specified by these three numbers. Okay. And the number of particles, the volume, and the temperature. And we want to relate this to the microstate will be described by a density in phase space. And we said that the density of phase space here should be given by this function. Okay, so what we said last time is that the density in the phase space must be a function of the energy of the Hamiltonian. And for a system in thermal contact with a heat bath, this function is the exponential. And this coefficient beta is 1 over kT. Okay? Now, I want to what I want to do is to derive this same result from a different perspective. And this perspective is the one where we really think of an ensemble of systems. Okay, so we think that we have so an ensemble, as we said, is a set of n copies of the system, and and now we are going to take a generic situation where this system can be in different energy levels, and we are going to consider discrete energy levels. Okay. So there are a certain number of energy levels of the system A, which I will label by R. And ER is the energy of the system in the Rth energy level. Okay. So now, if we have n, so we have all these copies. So in our ensemble, we have n copies of the system, and we are going to consider the limit where this number is very, very large, goes to infinity. Okay. So we have a density of points over this energy level, over the states of my system. And so of these big n copies, n of R will be the number of copies in state R. Okay. And of course, this will satisfy the condition that if you sum over all the states, then you should get big N. Okay. Now, what we want to do is to derive the probability to find the system in a certain state R. Let me call it PR. And we know that this must be a function of the energy of the level. I mean, this is by Liouville theorem. Okay. So we know that this will be a function of ER, and we want to rederive this result, which essentially tells us that this is e to the minus beta times ER divided by a normalization constant. Okay. So I want to rederive this result, and the way to rederive this result is to, I mean, in our ensemble, what is the probability that you will be in state to be in state R? Is exactly the fraction of copies of your ensemble which are in state R. Okay. Okay, so we have to compute. We have to essentially compute this number, the fraction of systems in the ensemble which will be in state R. Okay. So it's a bit of an abstract. It's a different point of view, but it's so today what I'm asking you to do is to think that really think about this gas of points which are defined on the phase space, on the space of all possible states of the system. And we are going to argue about what is the fraction of these copies of the system in the ensemble which will be in any particular state. Okay. And so if I want to compute this probability, of course I will. I'm considering a system which is in thermal equilibrium with a larger system. So so the average energy, so the energy of so the energy of my system will be so each of these systems will have an energy ER, but so this since this subsystem is in equilibrium with the other system, there will be a distribution of energies, okay, in my ensemble, and there will be a certain average energy, okay, because if and the energy density in my system will correspond to the energy density in my so will be fixed so that if it is larger than an equilibrium value, then there will be a transfer of heat to the heat bath, and if it is lower than a certain value, there will be a transfer of heat from the heat bath to the system. Okay. So, in general, we want to discuss the system where the problem where this number of copies, well, this distribution of the copies of the ensemble on the energy, on the states of the systems, is such that it satisfies this condition, and also that the average energy is also a fixed number. Okay? And this U will be the average energy. Okay? Okay, so so what is the probability that I will find so the state of my ensemble will be specified by all these numbers, the collection of all these numbers. So this will specify the state of my ensemble. And what is the probability that, and you have to think that any assignment of these numbers which satisfies this constraint and this constraint, we want to give to this assignment an equal probability. Okay? So the probability to find a particular assignment, a particular distribution of the copies in the ensemble on these states will be equal to the number of ways in which I can distribute the different systems in the ensemble in these many states. Okay. So this probability will be proportional to, and this the number of ways in which I can distribute these n points into these states will be essentially given by the multinomial coefficient. Yes.
Can you repeat this point?
Okay. So I'm asking you to think about an ensemble as a gas of points in the phase space of the system. Now, my phase space is a phase space which is discretized. So there are cells or states, and each of these cells is labeled by R. And it has a certain energy. This system inside this cell has a certain energy, ER. And in this gas of points which describe my ensemble, there will be a certain number, NR, of points which are in this cell, which are in this state. Okay? Now, what I'm interested in is in the way, in all the ways to distribute these points in the phase space such that this condition is satisfied, the total number of points is n, and the average energy is U. Okay? And okay, so if there is a certain set of numbers, by this I mean really n0, n1, n2, etc. So the number of system copies of points of the ensemble in state 0, the number of copies in state 1, etc., etc. So for any of these numbers here, there is a way in which I can assign the points which correspond to these numbers here. And this number is this one, okay? So the larger is the number of ways in which I can distribute these points in the ensemble in this way, in this particular way, the larger will be the probability to find the system with this distribution of points in the phase space. Okay? So you should think this is really the distribution of your points in the this n of r is really your density on the phase space. Okay? Actually, n of r divided by n is precisely the density of points in the phase space. Okay? And when I'm writing this, what I'm saying is essentially any way to distribute my copies of the ensemble in the phase space has the same probability. So a particular distribution of points in the phase space has a probability which is proportional to the number of ways in which I can put these many copies in the phase space in such a way that there are nr points in state R. Okay? Okay. And then what I want to do is to compute the density by taking the limit when the number of copies goes to infinity. Okay. Now, so if I want to compute so let me call this number W of the distribution NR. So if I want to compute for example, the probability of state R, the probability of state R will be essentially the probability, so it will be essentially the average number of points which are in state R in my ensemble divided by n when n goes to infinity, when this large n goes to infinity. And this average should be computed with this probability. So this will be the sum of all ways of distributing my points in the phase space times this W of nr times nr normalized by the same thing. One over n. Yes, thank you. Okay. So this is the calculation that we want to do today. And the reason we want to do this calculation, there are many reasons because we want to do this calculation. One is that there are, you will see mathematical techniques which are used over and over again in statistical mechanics, so it's better you get familiarized with it. And the second one is that there is an important concept that we can compute this number in two ways. Actually, we can compute this number in this way, but what we can also do is to compute the probability that to consider instead what is the most probable distribution of phase space of points in the phase space, and call it n star of r. And from this point of view, you can define a different, another probability of for state r. And what I want to show is that these two probabilities are the same. Okay, so that essentially the average over all the ensemble is essentially dominated by the most probable points in the ensemble, the most probable distribution in the ensemble. Okay. Yep. No, it's not the mean. It's really what makes this number maximal under these two constraints. Okay. So let yes, so let us start by computing the most probable distribution. So the most probable distribution is the one that makes maximal. It maximizes n of r, the number of ways to distribute the points in the ensemble corresponds to that distribution, subject to the constraint that sum over r of n of r must be equal to n, and sum over r n of r times E r is equal to u times n. Okay, so this is a simple problem, and actually it's better to study the problem of the maximum of the log of w over nr, because the log of w of nr is the log of the multinomial coefficient, so is the I can write it as n log of n minus sum over r, n of r log n of r. This is using the Stirling approximation. Okay, using the Stirling approximation, this is what you get. Okay. Now I want to look for the maximum of the distribution n of r, which makes this object maximal. So imagine that the maximum is called n star of r. So I want to take n of r equal to n star of r plus a small fluctuation. And I want to find these small fluctuations in such a way that the change in w is always negative. Okay, the first derivative is 0. Okay, and so if I substitute here for this thing, I will get n times log of n minus sum over r n r star log n r star. And then the first order term will be sum over r of log n r plus 1 times delta n r. Okay? Now, where this is just the derivative of this with respect to nr. Okay? So when I take the derivative with respect to nr, you get log n, and when you take the derivative of the log, you get nr divided by nr, which is 1. Okay? And there are or higher order terms. Now, what I want to do is to consider this distribution, find the distribution which makes this maximum, means finding the distribution which makes this the change in W stationary with respect to delta n r. Okay. Now, however, I have to consider that I have to find variation in delta n which also do not violate these constraints. Okay, and these variations are such that the sum over r of delta n r must be equal to 0, and the sum over r of ER times delta nr must also be equal to 0. Okay. So, in general, if I want to look for the maxima of this function subject to this constraint, I have to look for a variation of delta W. Variation of delta W, for which these equations are also satisfied. Okay. In order to do this, what I have to consider are variations of. I have to consider I have to introduce Lagrange multipliers, okay, and to consider that the variation of the log of W plus alpha times sum over R and R, sorry, call it beta, minus alpha sum over R and R, that this must be 0, okay? And so if I do this, I have that this variation here is proportional to minus the sum over R of log nr star plus 1 plus beta ER plus alpha. This must be equal to 0. Okay, so you see now for any given beta and alpha, this variation must be 0 for all values of delta n r, for all possible variation, And this ensures the fact that I mean, these values of alpha and beta will correspond to a particular value of n and u. For that particular value of n and u, then this the w will be maximum. The log of w will be maximum. Okay. So and if you do, so what you have to solve in order to find to solve this equation for any delta n is just to solve this equation, and what you get is that nr star is equal to e to the minus beta times er times a constant. Let me write it properly. E to the minus beta times er. And this constant and this value of beta will be adjusted in such a way to satisfy these two constraints. So in particular, so the constant will be just e to the minus beta times er, such that this constant z of beta is the sum over all the states of e to the minus beta er. This is just the normalization constant. And the value of beta will be such that if you sum over all the states the energy of state r times nr star, which is e to the minus beta er divided by z of beta, this will be equal to u times sorry, there is an n here, and okay, z beta is given by that. Because the number of copies in state R will be proportional to the total number of points in the ensemble. Okay, so I have defined this z of beta in this way, so that. Okay, so this this is an equation. This is an implicit equation for beta that you have to solve in order to satisfy this constraint. Okay. So you see that this canonical ensemble, which we have discussed on Monday, actually comes out from considering the most probable distribution in n star. Okay. Now the second thing I want to do is to show that it also, if you consider the average distributions, that is, if you consider taking an average over all possible ways to distribute your ensemble in the phase space consistent with the constraint, you will get the same result. Average value. So let me call this average value nr. So this average value of nr is, by definition, is the sum over all the nr times this w of nr times nr divided by sum over nr W of NR. Okay. Now I want to introduce a trick which is very common, and is that of introducing a generating function. So when you have to compute an average like this one, this is a very complicated object. So it is convenient to introduce an object which is the sum over all the n of r of w of n, which is n factorial divided product of r n r factorial times the product over r of omega r to the n r. Okay. So this notice that this sum should all be sums such that this n of r satisfies the constraint. So you should think about these sums over nr as a sum over all the n of r such that the sum over r of nr is equal to n, and the sum over r of nr times er is equal to n times u. Okay. So it's a sum over all possible distribution of all possible distribution of occupation of the states which are consistent with the constraints. And actually, the fact that there are these constraints makes life complicated. Now, why is this thing simpler? Because, for example, if you are able to compute this object here, then you can readily verify that if you take omega times the omega r of the log of gamma, then you get, and then you compute this when all omega r are equal to 1. So you take this object, you take the log, and then you take a derivative with respect to omega r, multiplied by omega r, and set all the omega r equal to 1. Then you get this. And why is it so? Because, when you take the derivative of the log, you will get 1 over gamma times the derivative of gamma with respect to 1 omega. The derivative over gamma with respect to omega r will get you an omega r down. And this omega r, and then you will get omega r to the nr minus 1, but with this omega r you will get back omega r to the nr. So essentially you will have the same sum here, but with an omega r inside. Okay? And when you set all the omegas equal to 1, all these factors here become equal to 1. So effectively, in the end, you get exactly the ratio between these two objects. Okay? So this is a very useful trick in statistical mechanics is one which is used over and over and over again. Okay. And indeed, we are going to use it even further, because well, the point is that it is hard to compute this. It is not easy to compute this sum because of this constraint here. Okay, so if there were no constraint on the energy, then if this sum here were just with this constraint here, then this would be very simple, because it's just the multinomial expansion of the sum of the omega r to the big N. Okay, but this constraint actually makes life more complex. Okay, so how are we going to solve this problem? Well, the way we are going to solve this problem is to, again, using a very similar trick, that is to compute a different function, which is a function not of u, but of z. And so what I'm going to do is to sum over all the values of u, all the possible values of u, of this gamma of n and u times z to the u times n. Okay? Now imagine that I can compute this function here. And imagine that the values of the energy are such that u times n is an integer. Okay? Then all I have to do in order to compute this number here is to get the power expansion, Maclaurin expansion of this function here, and to compute the coefficient of z to the un in this function here. Okay, and this is given by the formula, which is 1 over 2 pi I, then an integral on the complex plane, which encloses the origin of g of n and z, divided by z to the n times u times n. Okay? So what I will do in order to compute this is first to compute this, and then use this formula to compute the coefficient of z to the u times n of g. Okay? Is this clear? It's a bit complicated, but it's a type of calculation which occurs over and over again in statistical mechanics, so we'll do it with some care at least once. Yes, we assume that u times n is an integer. You see, u are, in any case, discrete levels, because I have a finite system, so there are discrete energy levels for my system. And n is as big as I want. Okay, so I can always find n such that this is an integer. Okay, so that is not the problem. Okay, so what we want to do is to compute this this g. And no, so now this G is the sum of all values of u of this gamma, which I can take from here, which is the sum over all this nr of n factorial. And now I have the product over r of u of omega r to the nr divided by nr factorial. And here I should multiply by z to the u times n. But inside this sum, I can use the fact that u times n is the sum over all the r. Here I can use the fact that z to the u times n is effectively, u times n is the sum over all the r of er times nr. So this is the product of z to the nr times er. Okay? So here I have z to the nr times er. Okay? And now what you see is that the sum over the u, and then there is a sum over the sum over u is just imposing that this is equal to this. But the sum over the u is not affecting anything, because this nothing here is a function of u. Okay. Okay, so the sum over u will just be equal to 1 for that u which satisfies this constraint, and will be equal to 0 for all the other. I mean, all the terms in this sum will be equal to 0 for all the terms which do not satisfy this constraint. Okay, so I can essentially get rid of this constraint in the sum, and I have only this constraint. So essentially, and this constraint is essentially with this term here. It's just giving me the multinomial expansion of the sum of over r of omega r z to the er to the n. Okay? Was this fast? So if you make this, if you expand this object here, you will get the multinomial coefficient times all the terms, all the monomials. Okay, so you will get exactly this term here. Okay, so you see, computing this function here, it's easy. It's rather easy. And actually, this function has a form, is a very peculiar form. What we have found is that this of n and z is the form of e to the n times function g of which depends on z, but it also depends on the omegas. And this function g. But no, let me write it just as sum of r omega r times z e r to the power n. Okay. So now if I want to compute the gamma of n and u, what I have to do is 1 over 2 pi I, the integral dz over z of this function here. So it's so if I write this as f of z to the power n, here I will have f of z divided by z to the u to the power n. This f z to the n is just g of nu, and then there is z to the u times n. Okay, now we have to compute this integral, and the peculiar thing about this integral is that it is an integral of something to the power n, and n is very, very large. Okay, so we anticipate that this function, so this function, this integral has to be evaluated, say, on a contour in the complex z plane, which encloses the origin, because of course there is a singularity in the origin, and you want to take the residue of that, and the coefficient of the power expansion of this is related to the residue of the function, and so now, however, if you consider this function, then let's consider this function on the real as z increases on the real axis. Okay. So now you see that f of z is an increasing function of z. Okay. So the part up here is will grow very, very fast. But z to the u is also an increasing function of z. Okay. So this is the product of an increasing function by a decreasing function. So so it's a function of z real. So the function f of u the function f to the power n will increase very, very fast. The function 1 over u to the u 1 over z to the u will decrease very, very fast. And there will be a minimum. Okay, there will be a minimum somewhere on the real axis. So let's call it x naught. Okay, so it means that there will be a point x naught on the real axis where there is a minimum going on the along the real axis of this function. Okay. Now, what is we can compute. Let us compute the what I want to convince you is that this point is actually a saddle, in the sense that if you now consider going through this point x0 on the imaginary axis, this point will be a maximum. Okay, so it is a minimum along the real axis, but if you go parallel to the imaginary axis, it will be a maximum. Okay, and the idea is that it is easier to see this if you instead of considering this function, you consider the log of this function. So let me define g of z as the log of f of z divided by z to the u, or minus u times log z. Okay, so of course, since g of z is the log of this function, if this function has a minimum, this will have a minimum. If it has a maximum, this will have a maximum. So it's the same considering this function as this function. Now, so the point x0 will satisfy the condition that g prime computed in x0 must be equal to 0. And now g prime, what is g prime of x0 is so is the log of f of z is f prime of x0 divided by f of x0 minus u times x0. So this is the equation for x0. Okay? Yeah. Yeah, it's a definition, yes. G of z is a definition, and is it's just the log of what is inside here. So essentially, I'm writing this as integral dz over z of e to the n times g of z. Okay? So this is, if you want, the definition of small g of z. And what I'm saying is that now g of z must have a minimum along the real axis on z. And I'm going to, and this minimum I call it x naught. And I'm looking for this minimum. Okay? And so this minimum satisfies this equation that if I look at the original definition of f of x, f of z, which is this one, the first derivative of f of z is equal to sum over r omega r x naught to the er minus 1 times er divided by sum over r omega r x naught er minus u over x naught. Okay, so the another way to rewrite this, you see, if I multiply by x, this is equal to 0. So the equation which gives me x0 is an equation which I can write as u is equal to sum over r omega r x naught to the er times er divided by sum over r omega r x naught to the er. You see, this is an equation which you already can see it's essentially telling you that x naught is such that u will be the average of the energy levels over a certain distribution. Okay. Okay, so this will give me x naught. Then, since this is a minimum, I will expand g of z around x naught. So there will be g of x naught plus the first derivative of g in x naught will be equal to 0, and I have only the second derivative. Second in x naught times z minus x naught squared plus higher order terms. Now the key point is that the second derivative of this function g is positive. Okay? And so in order to convince you of this, so the first, so let's compute, so this is the derivative with respect to z of sum over r omega r z to the er minus 1 times er over z over sum over r omega r z to er minus u over z. Okay, so let me write this as take out 1 over z in both of these two terms. So this becomes u, and this is a 1 over z. So when I take the second derivative, I can take the second derivative here, or the second derivative here. So when I take the second derivative here, I will have minus 1 over z times this thing, which is equal to 0 at x naught. Okay? So this part will not contribute when I compute it at x naught. The part which will contribute is only the second derivative of this term inside, which is essentially, since this does not depend on z, it's just this term here. And you can, if you do this calculation, well, there is a term which is sum over r of omega r z to the er. When I take the derivative up here, and this is just omega r z to the er minus 1 times er squared. And then there is a term, and this is multiplied by 1 over z. So there is a 1 over z here. And then there is a term where I take the derivative with respect to this, which would give me this squared, okay, minus sum over r omega r x naught over z er minus 1 times er over sum over r omega r z to the er squared. Okay. Now, when I compute this and at x naught, as I told you, so this term will be equal to 0. Yep. This one should be square, you're right. Thanks. Yes, you're right. And here I forgot also the term, the factor 1 over z there. Very good. So when I compute it at x naught, this term will be equal to 0, as we said. And this essentially will be equal to u squared. Okay, so it is, and actually you can check as an exercise that you can write this as sum over r omega r er minus u squared times z to the er divided by sum over r omega r z to the er, x naught. times 1 over x naught squared. Okay, so if you expand this square, you will see that essentially you get this term and this term here. Very good. So, so the important point of this thing is that this is positive. This is a positive quantity. Okay. So this is a positive quantity. So now we want to see. What I want to show you is that in the neighborhood of this point. I mean, yes, this is positive in the sense that if z is real along the real axis, then this will be a minimum because the second derivative is positive. But now if I put z equal to x naught plus iy, then this, so I move along this direction here, then this term will be negative. Okay, so with respect to y, that will be this will be g of x naught minus 1/2 g double prime of x naught times y squared. Okay, so it will be a maximum. Okay. So, which means that if in order to compute this this integral, what I can do is to compute an integral when on a circle of radius x naught. Okay, so I will compute this integral by doing it on this contour, where this is the point x naught. So in other words, I will take z as being equal to x naught times e to a face. And for convenience, let me write this as I theta divided by square root of n. I introduce this factor square root of n because of convenience. So the dz over z is, when I take the differential, I have I d theta over square root n. Okay? Sorry. So this integral here becomes the integral from minus pi times square root n to pi square root n in d theta over square root n times 1 over 2 pi. And then I have E. Then I can use these expansions here. And if I use if I use this expression for z, for n large, this will be g of x0 plus 1/2 g double prime of x0 times x0, which multiplies 1 e to the I theta over square root n minus 1 plus higher order terms squared. So you see that this is I can expand this if square root n is if n is very, very large. I can expand the exponential. So this is g of x0. To leading order term, this will be minus 1/2 g double prime of x naught x, sorry, there is an x naught x0 squared times theta squared over n. Okay? The minus comes from I squared. No? And now if here I have e to the n times g of z, which is n times g of x naught minus 1/2 g double prime of x naught squared times theta squared, plus higher order terms. And you can figure out that the higher order term will be very, very small compared to this. So you see, this does not depend on theta, and you can take it out. And this, what you are left here is just a Gaussian integral. A Gaussian integral which you can actually extend to from minus infinity to infinity, because it goes from when square root n goes to infinity. So the final result is that this gamma of n times u is e to the n times this g computed in x naught. And then there is the Gaussian integral, which is going to give me 1 over the square root of 2 pi n times the second derivative g double prime of x naught times x naught squared. Okay? And well, this is an approximation because there will be higher order terms here, which are of order at least 1 over square root of this n. Very good. So you see, now we can go back to our original problem with this formula. What we want to do is to compute n of r. And what we said that this thing should be given by omega r, the derivative with respect to omega r of the log of this gamma of n and u. So this is, and then I should compute this at all the omega equal to 1. Put all the omega equal to 1. Okay? So this is omega r times the derivative with respect to the omega r of, now you see the log of this is n times this, and then there is the log of this opposite, which is much smaller than this. So that to all practical purposes, when I consider if I want to compute n of r divided by large n, then the log of this term will go away. Okay, so to all practical purposes, one can just take n times g of x naught. And neglect the log of this term. Okay, that will be small compared to this one. And then you should set the omega equal to 1. Okay, so what is what do we get as a result? Well, we should remember what was this g of x. So G of Z was the log of the sum over R omega R times Z to the ER minus U over minus U log Z, right? Okay, this was the definition of the function G of Z. So if I want to compute this derivative, so the n of R will be n times omega R. Now in this derivative there are two things. One thing is when I take the derivative with respect to omega here, okay? And that is going to give me E Z, so x naught to the ER divided by sum over R omega R x naught to the ER. Okay. Now the other thing is that x naught also depend on the omegas. So I should take the derivative of G with respect to the x, to respect to x naught, and the derivative of x naught with respect to the omega R. Okay. I should take the derivative of, I should take G prime of x naught times the derivative of x naught with respect to omega R. Okay. However, we have seen that this is equal to 0 because we are at the saddle point. Okay, so this term is equal to 0, and then I should put all the omegas equal to 1. So the result which I get is that if I set all the omegas equal to 1, is that this is just n times x naught to the power ER divided by sum over R of x naught to the power ER. Let me say R prime. Where this x naught is determined by the condition. Is determined by the condition, exactly by the condition that this thing should be equal to 0. Which is the constraint which fixes the average energy. Okay. Now, this is the final result. So you see now, if I call x naught equal to e to the minus beta, then this equation is equal to the equation which I had to the Boltzmann to the canonical ensemble we have derived previously. Okay, so this shows you that that if you so this shows you that essentially under this assumption, I mean, if you put x naught equal to e to the minus beta, then you can see that this is n times e to the minus beta ER somewhere R prime e to the minus beta ER prime. And the equation which fixes beta, you will see, is exactly the same as the equation which fixes beta in the previous calculation which we have done, where we were looking for the most probable values of this NR. Okay? So the fact that this is equal, exactly equal to this, the average value of this occupation number in the ensembles are exactly equal to the most probable values. means that the distribution of this distribution in the phase space is very, very much concentrated. Very much concentrated on the most probable values. Okay? And as you see, I mean, computing, in many cases, computing the most probable value of a distribution is simpler than computing the average. Okay, so this is also computationally very, very, very efficient. So this is essentially what I wanted to show you today. It's all in your lecture notes, so it's you can follow all the passages. They are very well explained, but I think it's important that you understand this type of calculation in detail, because it's contains, I mean, it's very the basis of statistical mechanics. So there are other questions?
The fact that we find that the most probable state is equal to the average, is it because it's an infinite number of microstates?
Yes, yes. So this is what we have used is that this is true when this n, the number of microstates, is very, very large. And we have used it both when we have computed this number here, because we have used the Stirling formula. You remember? And we have used it when we have computed this number here, because essentially we have done this expansion around the saddle point. And so around this point x naught, when we were considering this the integral on the contour. We have done the expansion on the saddle point, and we have seen that around the saddle point the function was very rapidly decreasing down, as soon as you move order 1 over square root n away from the saddle point. And then, so in both cases, both this calculation and this calculation are valid when this number of points in the ensemble is very, very large. But in any case, the ensemble is defined when this number is infinite. Okay, so this is a good approximation, right? Yeah. Yeah.
Does it also hold when it is away from equilibrium?
No, I mean, whether this calculation is true when we are away from equilibrium. This calculation is it's assuming equilibrium from the start. Okay, so we are, I mean, when you have a non-equilibrium system, then you have a system which is following its dynamics, and it's going to eventually go to the equilibrium, right? Here there is no dynamics at all. There was no dynamics at all. So we were already assuming that the system is in equilibrium, and that there is a distribution over the phase space, over the possible states of the system that describes the equilibrium system, and we were looking for this distribution. Now, if you have a non-equilibrium system, then it is not true that it is not true that you have all the states of your ensemble equally populated. So let me take an example. So imagine that you could think, so I mean the gas in this room, or so the gas in a gas in a box with a fixed energy. Okay, you can consider the configuration of this gas when all the particles are just in half of the room, in half of the box. The other half is empty. And you can consider configurations where the energy is exactly the same. Okay, so if you so this is a very non-equilibrium situation. It's a situation of non-equilibrium. Okay, in the sense that if you leave the system do whatever you want, it will expand to the whole gas, right? Now, if you consider the microcanonical ensemble, so those particular states where all the particles are only in half of the box will have the same probability as any other configuration with the same energy. Okay. So the reason why you are not in equilibrium is because in your ensemble, in the ensemble which is corresponding to what the initial situation, only the states where the particles are in half of the box are populated. Okay, the others are not populated. Okay. However, if you let the system evolve, it will evolve most probably to states where the particles are everywhere in the box, because these are the most numerous ones, the most probable, many more than the initial ones. Okay, so this is the way in which you can think of non-equilibrium phenomena. Okay.
Can I work backwards from this, and if the value that we measure, the average is the most probable one, does it imply that it is in equilibrium?
So if
so if this holds, then can I go backward and see if it is in equilibrium?
so if okay, so you're saying yes, if the average value is equal to the most probable value, if it is not, then yes, it depends on what are you taking that average there. So if you have a distribution over the energy levels, and if that distribution is not such that the average number of points in the ensemble is not equal to the most probable one, then you are not in equilibrium. Yes. Yes. Okay. So see you on Friday.